Today we're going to look at sketching reciprocal functions. Now these are functions that take the form 1 over x or 1 over x squared, etc, etc. Now I should really complete this by saying that x cannot take the value 0 because, well, maths would break at that point and we can't define 1 over 0 because it just simply doesn't work. What we would need to draw on our graph would be a dotted line, which we would call an asymptote. A-S-Y, why is that gone like that? A-S-Y-M-P-T-O-T-E, an asymptote. These are simply points on our graph that we can't evaluate. Now let's start investigating this function. We know 1 over 1 is going to be the point 1. Let's start taking larger values of x. So if we did 1 over 2, the function would evaluate to 0.5. If I did 1 over 10, then the function evaluates to 0.1. And actually, the larger I make the value of x, as x tends towards infinity, the function is going to get smaller and smaller and smaller, so the function tends towards 0. Now I can work that argument round the other way by making x very, very small. So if I take x to be 0.5, then I'm going to get 2. If I take x to be 0.1, then I'm going to get 10. And this time, if x tends towards 0, the closer x gets to being 0, then the larger my function gets. Then f of x tends towards infinity. How do we take this information and draw it on a graph? Well, as x tends towards infinity, the function tends towards 0, so I've got part of my graph that's going to lie here. As x tends towards 0, then the function tends towards infinity, so that gives me my part of my graph here. And I simply join the points together with a smooth curve in between. Now it's worth noting here, as I talked about earlier, these asymptotes, that the function can never actually touch the y-axis in the same way that it can never actually touch the x-axis, because no matter how large we make x, 1 divided by whatever that value of x is going to be is never going to be 0 itself, in the same way that I can't let x be 0 because I can't define the function at that point. What about for negative values of x? Well, negative values of x simply look like this. And that's what we have summarized on the next page. So my 1 over x graph is the graph on the left, and my negative 1 over x graph is the graph on the right. Now let's think for a moment what might happen if we did 1 over x squared. Well, if I square the value of x, it's always going to be positive. Now I still have this idea that as x tends towards infinity, then the function should tend towards 0, but it just so happens that that would keep both values positive, and that's exactly what we've got here. So as x tends towards positive infinity, the graph tends towards 0. As x tends towards negative infinity, the graph also tends towards 0, but again from the positive side, because we are squaring that negative value to make it positive. If I look at the minus 1 over x squared graph, it's simply a reflection in the x-axis, and that's something that we should be familiar with. The last thing that we want to do is to consider how to draw two of these functions on the same graph. It's all to do with how big the value of k, or the constant value on top, is, and that's going to tell us whereabouts our functions lie. Now, we know that these are positive 1 over x squared graphs, so I'm going to have a function like this. And the first function that I've drawn on here, I'm going to call y is equal to 3 over x squared. And if I think about 7 over x squared, well, 7 over x squared is just going to be the same shaped graph, just slightly further away. So there's my same shaped graph, just slightly further away. And the larger the value on top, the further away my graph is going to be from this central point at 0. So this function here would be my y is 7 over x squared. And that's all we have to say about reciprocal graphs.